everyone. I'm very excited to be here today and present my research about Windows error reporting. But first, a little bit about myself. I've been doing security research for Palo Alto Networks for the past 4 years for the anti-exploit team here in Tel Aviv. I'm interested in fuzzing, vulnerabilities, exploits, and mitigations. And as the video just showed, I've also been acknowledged as Microsoft MSRC Most Valuable Security Researcher at the 10th place for the past 2 years. Now today, first, we'll start by explaining what are privileged file system access bugs. Then I'll give an overview of the Windows error reporting architecture. And finally, I'll show some vulnerabilities I discovered in Windows error reporting and how I exploited them. So the first thing you need to know is what happens when you access files in Windows. Let's say that we have the process gdl.exe that runs as a standard user on the system. And gdl.exe tries to open the file cwindows system32 drivers pci.sys for writing. Now, when you create or open a file in Windows, your access token is compared against the security descriptor of the file. So I used the DACL tools of Windows to show the security descriptor of pci.sys, and it shows which groups and users can access that file and how. For example, the anti-authority system group has full control over that file. That's what this F stands for. And it means that a process running under this group can read, write, execute, delete the file, and do whatever it wants. And as opposed to that, a process running under the built-in users group can only read and execute the file. So gdl.exe running as a standard user that's part of the built-in users group, if it tries to open pci.sys for writing, it will get an access denied error. And as opposed to that, let's say that we have another process on the system that's called mysrv that runs as local system. And because it's part of the anti-authority system group, if it tries to open that file, it will succeed. So what are privileged file system access bugs? This is basically asking some privileged components, such as a service or a driver, to access a file for us that we couldn't access otherwise. And I want to show you first, before digging into where, a very simple example of that. Let's say that mysrv.exe from before is an example of a Windows service, and that this service exposes an RPC interface, which is a way to call it from other processes. And that RPC interface has one function in it that's called please write file for me, that gets 2 arguments. One is a file path, and the other is a buffer. And let's say that when you call this function, mysrv.exe would just open or create a file for writing and write the data to it. And this process runs as local system, and if you're familiar with RPC, you probably know the concept of impersonation, which means that mysrv.exe, when doing certain actions, could swap its token temporarily to the token of the caller, gdl.exe in this case. But let's not dig into this and say that mysrv does not do it. So if gdl.exe as a standard user would call this API and ask mysrv to overwrite pci.sys, it will just do it for him. And this is obviously a security vulnerability because, as I showed you before, as a standard user, you cannot access this file. So this is the basics, but you usually don't see these kind of bugs anymore in nature. Though you do sometimes, but they're very rare because the developers of services are usually aware of the fact they should not grant arbitrary access to files without impersonation through RPC. So there's another subclass of this vulnerability which is way more common. Let's say that mysrv exposes yet another RPC interface or RPC function that's called WriteLogFile. Now, this function gets 2 arguments. One is a file name, and the other is a buffer. And what it will do is create or open a file under the clogs directory with the name of your choice and write the buffer into it. Now, I dumped the security descriptor of the clogs directory. And it shows that the everyone group on Windows has full control to it. So basically, almost any process on the system, any user in the system can write data to this directory. So on its own, this bug does not seem like a security risk, because gdl.exe running as a standard user could just write to the file clogs.gdl.log. It can also ask mysrv to do that for him, but it makes no difference. But this is in fact not true. And if I wanted to exploit this vulnerability, what I'll do, from gdl.exe, before calling that RPC interface, I'd create a file system link. For example, an NTFS hard link between the file clogs.gdl.log and pci.sys. Now, I can do that despite the fact I have no write control over pci.sys. This is not needed for creating the link. And on its own, it's not a security risk, because even after I created this link, if I try to open the file clog.gdl.log, my token would be compared against the security descriptor of PCI.sys, and I'd still get an access denied error. But what if, after creating this link, I'd call the WriteLogFile RPC function? In that case, my SRV.exe would open the file clog.gdl.log, but it will actually open PCI.sys. And it has full control over that file as opposed to gdl.exe. And it will succeed, and it will just write the buffer to it. So this is how I'd exploit this vulnerability. And this is way more common because developers are sometimes not aware of the fact that you can redirect file system access using links when they write their code. So just to give a more general definition of this bug class, I showed you just one example. So I'd call this bug type a case where a privileged component, such as a service or driver, operates on a file, and it doesn't have to be wind into the file. It could be reading it, deleting it, modifying the security descriptor, and so on, as a local system with no impersonation on a path that's either controlled or can be redirected using a link. So what can you do with this type of bugs? These bugs could lead to privilege escalation. And a classic example of how to do so would be overriding some Windows executable that you have no write access to, and then get it running somehow as local system. Like if you overwrite some DLL file by a Windows service and get it running. And this way you can run any code you want. Now, 2 disclaimers before we dig a little deeper. The first one is that on a modern Windows installation, you cannot create file system links unless you're running at least at medium integrity level. So these bugs, if they involve links, are not relevant for these cases, like running in a browser sandbox, but they're still viable to some other cases. And finally, Windows added a mitigation only to the Windows Insider preview, which is like the beta version of Windows, in April of 2019, that mitigates the creation of NTFS hard links. You cannot create a link to a file unless you have write access to it. But this still didn't make it to the stable release, and also there are other type of links that you can use that are not affected by this mitigation. So now I'd give an overview of the Windows error reporting, but first I want to tell you the story of why I got into looking at this component. So at the beginning of last year, a researcher that goes by the name Sandbox Escaper or Polar Bear discovered many bugs of this kind. And what she did, she just released the source code of her exploit despite it weren't fixed at the time, so anybody could look at it. And from whom of you have worked the security industry, this was quite of a big deal. You probably heard about it. And one of the bugs she disclosed was in Windows error reporting. And as part of my job at Palo Alto Networks, I looked at that exploit and analyzed it. And then I decided to dig a little deeper into Windows error reporting and found a few other bugs of my own. So the first thing we need to talk about is what happens when a process crashes. Let's say that gdl.exe running the following assembly instructions, XOR array x, move the reference array x 1337. This will lead into right into the null page, which will get it crashing. And after it crashes, unless there's some other exception handler installed on the way, it will end up executing the unhandled exception handler in kernel base, which in turn will call where p report fault. Where stands for Windows error reporting, and where pre-report fault is our entry point into Windows error reporting. And the first thing it will do, it will try to make sure that where SVC, Windows error reporting service, is up and running. That service starts on demand each time a process crashes, and it goes down after a while if nobody communicates to it. And it's not really important. The way to do that is to write to the WNF name where service starts. Anyway, after this service is up and running as local system, gdl.exe or the crashing process would start communicating to it using ALPC, which is an inter-process communication mechanism in Windows. You can just send buffers between processes. And it will have where SVC call the function SVC report crash, which, as its name hints, its purpose is to report a new crash on the system of gdl.exe in this case. Now, I won't go into all the details about what it does, but it ends up calling create process as user to start the process that most of you probably know and is called wherefault. Wherefault.exe is the worker that does the actual work of Windows, of reporting a new crash in the system. And there are two things I want you to know about the creation of where fault. The first one is that WhereSVC uses create process as user API, which allows it to change the token of the newly created child. So it will be created, let's say if GDL.exe crashed and it ran as standard user, then it will use GDL.exe token to start WhereFault as a standard user as well. The second thing is that WhereFault is actually created as a child process of the crashing process, GDL.exe, and not of WhereSVC. And there are certain arguments you can pass in create process API in the startup info that allowed you to create processes as child of others. Anyway, once WhereFault started, it will do the actual work of collecting the data regarding the crashing process. This includes the list of loaded modules, the exception info, a memory dump, and so on. And once it's finished and finalized the report, it will write it to disk. There's a certain directory on your system under C program data Microsoft Windows Where, and there are 3 directories in it. One is the report queue directory, and WhereFault will create a new report subdirectory especially for each report, in this case the AppCrash.gdl directory, and it will put a few files into it. There's one file that is a mandatory file that it's called report.where, and is an INI file that describes all the metadata regarding the crash. Sometimes WhereFault will put more files in this directory, like a memory dump. Anyway, once the report is finished and written to the disk, WhereFault will do the actual work of uploading the data to Microsoft, and if it succeeds, it will move the AppCrash.gdl directory, that report directory, from the report queue to the report archive. And by this point, both of these processes will be done and exit. Now, there's one more thing I want to tell you about Windows error reporting. What happens if a process crashes when you have no internet connection? In this case, obviously, WhereFault cannot upload the data to Microsoft. So what it will do, it will just keep the report directory under the report queue. And at a later time, the Windows error reporting queue reporting schedule task will execute. And this task runs on demand under certain conditions, like when you connect to a new network or when you log in. And that schedule task will run the binary where mgr.exe-upload command line as local system. And it will enumerate all the reports directories under the report queue, if there are any, parse the report.where files, and upload the data to Microsoft the same way WhereFault does. This is basically all you need to know about Windows error reporting for the attack surface for the bugs I'll show later on, but there's much more into it. I didn't have the time to tell everything. But first, before we look into the bugs, I want to tell you why is Windows error reporting prone to privileged file system access bugs, like I showed in the first section. So first of all, many of Where's components run as local system. This includes WhereSVC, where-mgr.exe from that schedule task, and also WhereFault sometimes, depending on the permissions of the crashing process. Next, by design, many of these components allow any user to interact with them. And this is actually, I think it's quite a good design decision, because Microsoft wanted to reduce the privilege level of WhereFault.exe, so it will be the same as the running process. But in that case, WhereFault.exe has to communicate with some of these components. So everybody has to be able to communicate with this. And this includes the WhereSVC ALPC port, which is writable for the everyone group. The queue reporting schedule task, for some reason, I'm not sure why, can be started on demand by any user anytime. And most importantly, cPro and Data Microsoft Windows Where and its subdirectories are writable for almost every group on the system. So we have this privilege component, we can interact with them, and we can put files into the Where and its subdirectories. And these privilege components do a lot of interaction with those files. So if we create a file system link at the right time, we might abuse them into accessing any files we want. And I'll show some of the bugs, and I'll start with a warm-up bug. It's just more simple, so I wanted to explain it first. And it is a bug that can be reached directly to the WhereSVC ALPC port in the function collect memory info. And its impact is not that great, but it allows you to overwrite any file you want on the system with WhereSVC permissions as local system with content that you only partially control. So let's see the flow to that bug. From xy.exe running as a standard user, we can communicate to WhereSVC using ALPC. Whereas VC uses raw ALPC, it doesn't use RPC, which is a serialization layer on top of ALPC. So I had to reverse engineer its protocol, but this is not really important because the message you have to send is very, very simple in this case. It simply starts with this message code. And what it will do, it will trigger the collect memory function in whereas VC. And the purpose of this function is to do like a task list of all the running processes of the system and fetch their memory usage. This is data that you sometimes want to attach on top of the report because the reason for the crash might be that the system was out of memory. So it makes sense to know what were the other processes running on the system and how much memory they used. But the problem is that Warefault, if it calls that API, might be running at a very low privilege level. And it won't allow it to query the data regarding processes that run as local system. So this is why whereas VC actually exposed that API. So it would do that as local system for Warefault. Anyway, let's take a further look at what collect memory info does. It will first create a temporary file with a random name. It uses getTemp file name to produce it under the whereTemp directory using the util getTemp file API. And it will just create the file, close it, and return its path. Then it will call the util collect system info function that will reopen that file for writing, collect the data regarding the running processes, and write it back onto the file. Now, as I said before, the whereTemp directory is writable for everybody, so we can create file system links from it. And the fundamental issue here is a vulnerable pattern that we see in many of these bugs. It's not the only pattern, but it's very common, where you create a file in a random name in this case, you close it, you open it again, and then you write to it. And the problem is that this is not locked in any way. You can create a file system link in between those two create files, because as long as a file is open, you cannot create a link from it. So only once it's closed, we'll be able to do it. And let's see how we exploit this bug. We'd call redirectory changes on the whereTemp directory. That allows us to get notified each time a new file is created under this directory, along with its file name. Then we'll trigger the ALPC call, which will call collect memory info. It will create a new file under the whereTemp dir, and at this point we'll be notified in exploit.exe, and we'll know what's the random file name. Now, from exploit.exe, we try to create a file system link between that file and PCI.sys, for example, a file we have no write control over and we want to overwrite. Now, we'll only succeed in creating that link once whereas VC closes the handle it has for that file. So what I'll do to increase my odds at doing it at the right time, I'll just create a link in a loop. And hopefully, by the time the handle is closed, I'll create a link. Whereas VC will reopen the file. And instead of opening the temporary file because of the link, it will open PCI.sys, and I'll overwrite its content. So this is quite a cool bug. And what I want you to take from it, first of all, is that many of these bug patterns, you can very easily spot them with procmon. So for this bug in particular, I did reverse engineer the whereas VC binary because I needed to know how to call that ALPC interface. But for some of the bugs of this bug class that I discovered, I simply used procmon and just used the GUI to do some operations on the system. Then I checked if a privilege process with no impersonation access files that I have write access to. And that might be a good indication for a bug. Not necessarily, it depends what it actually does and if it checks if it's a link, but I think this is a good way to find these bugs. Finally, I never exploited this to full privilege escalation because it would require a greater degree of control over the file content. But this is still enough from MSOC to assign a CVE. The next bug I want to show you is quite better. It's a vulnerability in WarmGR PreparePathForDeletion, and its impact is that it allows you to modify the security descriptor of any file you want as local system and basically add write control to that file for your own user. This is better because then we have a full control over the written content to the file if we open it later on. Now, I discovered it, and Polar Bear also found it, but from Microsoft Advisory, you can see that Microsoft is aware that this has been exploited in the wild. So I assume some other group discovered it also and used it as a zero-day, which is pretty cool. So to reach that flow, we'll have to run the queue reporting schedule task that will start WarmGR as local system, as I told you before. WarmGR will enumerate all dependent directories under the report queue directory, And let's say that there's one report directory in it. So it will read the report.where file and parse it data because it wants to upload that to Microsoft. And what happens if that report data is corrupted? It could be just an empty file, invalid INI file, or even if WarmGR is not happy with some of the fields in it. In that case, WarmGR will decide to discard the report because there's no point at sending a corrupted report to Microsoft. So it will want to delete it from disk because otherwise it will just waste storage space forever. So it will call the util recursive remove directory function, which its purpose is to enumerate all the files under the upcrash directory and delete them one by one. But before actually deleting them, it called the function PreparePathForDeletion on them. And the purpose of PreparePathForDeletion is to make sure that the security descriptor of the file we're about to delete has delete control to the local system user. So Microsoft just modified the security descriptor and then deleted the file. And let's take a deeper look into that function. It gets a single argument, which is a file path. It then calls getFileSecurity API to fetch the security descriptor of that file from disk into memory. It then calls many API to tweak that security descriptor and add delete permissions to the local system user on top of the existing security descriptor. And this is very important. And finally, it will call setFileSecurity to apply that security descriptor back onto the file from memory. So there are a few problems here. The first one is just like the first bug I showed you. Those two APIs get a file path and not a file handle. So the file is in fact open twice. One time when we fetch the security descriptor and another time when we set the security descriptor. The second, and we can create a file system link in between those two and read the security descriptor of one file and apply it to another. The second thing is that we fully control the original security descriptor of the file because we create it. So you don't really care about the middle part. Just think about it as we could read the security descriptor of one file, copy it, and apply it to another. And I'll show this into more details. To exploit this, I'd create a fake report directory under the report queue directory with a malformed INI file. Then I'll call the queue reporting schedule task that we want WarmGR's local system. WarmGR will read the report, parse it, and understand that it is corrupted, and it will trigger the vulnerable flow. It will then call getFileSecurity on that file. And that security descriptor obviously allows write control to the standard user because it created it. Now at this exact point, we'd try from exploit.exe to create a file system link between the report.where file and a file we want to overwrite, like PCI.sys. And if we did it at the exact right time, then the newly created security descriptor will be applied onto that file using the file system link. So WarmGR can do that because it has full control over PCI.sys. It can modify its security descriptor. And if that occurred, then we'll now be able to open PCI.sys for writing and just write whatever we want into it. And this is a very handy exploitation primitive. Now, I always get a few questions about this exploit when I explain it. The first one is, does WarmGR later delete PCI.sys? Because as I told you, the entire purpose of this flow was to make sure that we can delete it and then delete it. So the answer is no for two reasons. The first one is that WarmGR actually had checks whether this path is a link before deleting it. And it's quite funny, but Microsoft didn't do it in the flow of changing the security descriptor. And that's quite good for me because I prefer that than deleting the file. And the second thing is that hard links just don't work that way. When you delete a hard link, it won't delete the target file, and we'll talk about it later. The second question is it hard to win the race condition? So yes, it's very hard to win the race condition. We have a very small time window where we have to create a link. But this is a logical bug. There's no corruption involved in here in any way, so we just don't care. We can run it for as many times as we want until it succeeds. And for my exploit, it took from a few seconds to 5 minutes on a 2-core machine, but I'm sure there are many things I could do to improve that. Finally, what file should we target to get code execution as local system? So basically, any DLL that will later get loaded as local system. And there's a very great technique by James Forshaw of Project Zero that shows how to do that. That still works today. So we don't have the time and won't go into details about it, but check his blog. Okay, now the final bug I want to show you for this talk is a bug in where DLL, where pclean where. And where DLL is some sort of a common utility that many of our components use. And the impact of this bug is that it allows you to delete any file you want on the system as local system. So first, I owe you something. I told you that file deletion bugs cannot be exploited using NTFS hard links, and I want to show you why. Let's say that from gdl.exe, I'd create a link between the file clog.gdl.log and C program files myapp.gdl.dll. For the myapp directory, I obviously have no write control because I run as a standard user. Now, after I created that link, let's say I have a vulnerability in mysrv.exe that runs as local system that has control over the myapp directory. And we will have it calling delete file on the path clogs.gdl.log. So you would expect that it would delete gdl.dll, but it just doesn't work this way. It will delete gdl.log. And the reason why is that hard links are like giving one file multiple names. And if you delete one name, you don't delete the other paths. So we'll have to use another links primitive, and we'll use something that's called directory junctions. So junctions are like symlinks between directories. We can create a junction between the clogs directory and the myapp directory, despite the fact we have no write control over the myapp directory. And even better, this still works for Windows Insider Preview, as opposed to hard links. After we created that, let's say that we triggered that bug that allows us to call delete file on the path clogs.gdl.dll. And that will actually delete gdl.dll in the target directory. I won't go into all the details about why, but this is because that the path rewrite actually works in the directory level. Any access to clogs would be redirected at that time, and the path will be replaced with C program files myapp. So this is better for us. And to create a junction, the source directory, clogs, must be writable, empty, and no open handles to it at the time we create the junction. And we'll see how this tackles us later on in the exploitation for this bug. So what's the flow for this vulnerability? Again, we'll have to run the queue reporting schedule task that will start wmgr.exe as local system. Then, from its main procedure, just before it exits, it will call the function where_dll where_pclean where. The purpose of this function is to delete all the old files under the where_temp directory. Sometimes throughout the reporting of a new crash, Wareful will write lots of temporary files under the where_temp directory, and they might not get deleted at some cases. So I think that storage space was in mind of the developers of Windows error reporting, and they wanted to make sure that these files get deleted at some point. And this is why we have where_pclean where. So what this function looks like? It gets no arguments, and it first fetches the path of the where_temp directory. This would return C program data Microsoft Windows where_temp. Then it gets the local time on the system. And then it will call util_prong folder of all files, passing those two as arguments. What this function will do is to call the find first file and find next file APIs that allow you to enumerate all the files in a directory one by one. And it will do that on the where_temp directory. And then for each file, if it is a file, meaning it's not a directory, and it is old enough, which is compared against the current time of the system, if the file is older than a week, it will delete it. So, and it will do that as local system, obviously, no impersonation here. So how can we exploit this into deleting files? It's very, very easy. All we have to do is create a junction between the where_temp directory and some other directory, like the C program files myapp. Then we'll run the queue reporting schedule task, and we'll get wmgr.exe to enumerate all the files under the myapp dir one by one. And it will just delete them. But it will do so only if those files are old enough. And at this point, I could actually stop, because this is enough for Microsoft to assign a CVE, but I wanted to write a better exploit. So what if I only wanted to delete a single file? For instance, only the gdl.dll file under the myapp directory, and keep the app.exe file. And even more than that, what if I wanted to delete this file even if it's not old enough? I mean, what if I was targeting a Windows directory with Windows binary for my exploit, and you just had Windows Update 5 minutes ago? Then my exploit won't work for a week, and I want to write an exploit that works on every day. So yeah, this would be better, and I won't go into details about it, but this is more likely what you want to do because it opens the possibility for a DLL hijacking attack, deleting only DLLs under some directory. So what I'll do to exploit this, from exploit.exe, run as a standard user. Again, let's say I target this directory and want to delete that DLL. I'll create some directory anywhere on the system that I have write control to. It doesn't matter. Let's say cmydir, and I'll put two files into it, a.txt file and gdl.dll. The second file name must match the same file name as the file that I later want to delete. Then I'll call the setFileTime API to modify the last write time file of these two files and set it to somewhere in the past. I can obviously do that because I have write control over those files. I just created them. Then I'll run the queue reporting schedule task that will run wormgr.exe as local system. And wormgr.exe will call util_getPath of wordtemp directory and fetch the path to the wordtemp directory. Now, at this point exactly, I try to create a junction between the wordtemp dir and cmydir. I can do that since wordtemp dir is empty, writable, and no open handles to it at the time. And if I did that, then the find first file API, it will still get called by the path wordtemp dir. But because of the junction I created, it will actually enumerate the files under the cmydir and not the wordtemp dir. And a little implementation deal about find first file, it opens a handle to the directory it's going to enumerate. So despite the fact that it tries to enumerate the path wordtemp dir, it will actually get a handle to the cmydir directory, because junctions does just work that way. Now the first file it's going to encounter is a.txt, and its last write time is obviously old enough because we just modified it. So it will decide to call delete file on the path wordtemp dir a.txt. But now, because of the junction, it will delete the a.txt file under the cmydir. Now, at this point, right before or after it deleted the file, from exploit.exe, we try to switch the junction between wordtemp dir and mydir to now point to wordtemp dir to my app. And I told you before there are three conditions that must be met in order to create a junction. Wordtemp dir must be writable, and it is. It must be empty, which it is to some sort. It's just a junction to another directory. And most importantly, there are no open handles to it. And this is because the handle that wormgr.exe has is actually to the mydir directory and not to the wordtemp directory because of the junction. So we can switch the junction at that time, and wormgr.exe will keep enumerating mydir and not wordtemp dir. And this is because the handle it has for the enumeration is actually to the cmydir, and it doesn't reopen the path, it doesn't reopen the directory each time it calls find next file. So the next file it's going to encounter is cmydir gdl.dll, and its last write time is obviously old enough because we just modified it. And it will end up calling delete file on the path wordtemp dir gdl.dll. And because we switched the junction, this will now point to cprogramfiles my app gdl.dll, and it will get deleted. So this is a very cool exploitation trick when you have a mismatch between a path and a handle. You can just change the junction each time you want, and wormgr will not be aware of the fact it's actually working on other directories. Now, still, this is quite a hard race condition. Is there a better way to win this race condition? We need to know when to switch the junction. Basically, what's the right time to switch the junction? The exploit still works despite that, but I wanted to write a better exploit. So I used a feature of Windows that's called opportunistic locks, or Oplocks. And this is a very cool feature of NTFS that allows you to lock files for access. It's mainly used for caching, basically delaying flushing a buffer to a file at a certain time, and make sure that no other entity accesses the outdated data. But again, I won't explain this too much right now. I'll just give you what you need to know to understand the exploit. So from gdl.exe, let's say I want to set an oplock on the file clogs_gdl.log. And to do that, I simply require a handle to clogs_gdl.log and a handle to a Windows event that I created. And after I set that oplock on that file, let's say that some other entity, like myserv.exe, that runs as local system, but it can be just any process running at any privilege level, it doesn't matter, tries to open the file clogs.gdl.log. But its thread doing so, calling the create file, will get blocked or set to waiting state because of the oplock we created. Now, even more than that, NTFS will kindly let us know, and it will set the event for that oplock that we created before. So gdl.exe will know that some other entity tries to access the file clogs.gdl.log. And now from gdl.exe, we can close the handle we have to gdl.logfile, which will release myserv.exe to do the file creation of clogs.gdl.log. Now, this is just the perfect feature we needed. This is a really cool feature. Despite, like, it's really cool. It's really good for exploiting file system race condition bugs. And the reason why it first blocks the file creation from the privileged entity, and it also notifies the unprivileged entity about the fact somebody is trying to access the file. And let's see how we can use it to our advantage. After creating the CMY directory and those two files in it and setting the last write time file, we will set an oplock on the path cmydir.a.txt. Then we'll trigger the entire exploitation flow. And at a certain point, wormgr.exe, because of the junction we created, will end up trying to delete cmydir.a.txt. Now, when you delete a file in Windows, you obviously first have to open a handle to it. And when wormgr.exe will open a handle to the file cmydir.a.txt, its thread will get to waiting state, and NTFS will just set the events for the oplock we previously set. So we'll know that wormgr tries to delete it, and we can take our time and switch the junction between where_temp_dir and mydir, so that where_temp_dir will point to the C program file's my app directory. And after we did that successfully, we can close the handle we have to cmydir.a.txt, which will release wormgr.exe thread. It will now delete the first file, but in the next iteration, it will actually follow the new junction, or junction we switched, and delete gdl.dll under the right directory. So just to recap, this is a very cool trick. Again, mismatch between a path and a handle, and using file system oplocks in order to know or to win the race condition constantly. So to conclude, where is a great place to look for privilege escalation bugs? It has a very large attack surface for these type of things, not only actually for file system access bugs, but to more stuff too. Now, if you're a researcher in this bug class specifically, I'd really recommend you use Procmon. It is a better use of your time than just reverse engineering binaries. Some of the bugs, again, I discovered basically by opening Procmon and crushing processes and seeing what's happening. Now, I only talked about 3 bugs I discovered, but I discovered way more vulnerabilities in Windows error reporting, and I'll publish more information about them in Palo Alto Network's Unit 42 blog in the next few weeks. So if you're interested in that topic, I recommend you review them. And finally, 2 things. The first one, I really want to thank James Forshaw of Google Project Zero. James did a lot of work on this bug class among some other types of logical bugs and published some really great posts about them. And even more than that, James also published a lot of really good tools that I used in exploiting these kind of bugs, and it really made my life a lot easier. So if you're looking into these kind of bugs, please read James' blogs and use the tools he published. And finally, a little note, originally I didn't know that, but in his talk here, Dave from Microsoft yesterday, he told that Microsoft will introduce 2 more mitigations that are related to file system link issues in the future. So those 2, plus the hard links mitigations, if they all make it to the stable release, might mitigate this entire bug class for bugs that require file system links. Some bugs don't, but most bugs do. So I think this is a really good direction, and I really wait to see how these mitigations look like when they make it to the Windows Insider preview. And that'll be all. That's my Twitter handle. I hope you liked the talk, and if you have any questions, then that'd be a good time.